Let's have a look at this question paper. It is a control test that was written last year. I downloaded this from the sternmorephysics.com. So the total marks is 75 and it is 1.5 hours. So that's about 90 minutes. It's always important to look at the instructions. For an example, check the number of pages. You are told the question paper consists of 9 pages and 1 page information sheet. Double check to make sure that everything is there. Another thing is to make sure that you round off your final answers, especially to 2 decimal places. So let us look at the first question. Question 1. It is multiple choice questions. 4 options are provided as possible answers to the following questions. Each question has only one correct answer. Write only the letter A to D next to the question number 1.1 to 1.5 in your answer sheet. So basically this means that if, let's say for question, perhaps you got question 1.7, your answer is E, you just need to write 1.7 and the letter. You don't need to mention the statement. Right. So question 1.1. The diagram below shows a transverse wave. Which one of the following represents X, Y, and Z respectively? Is it A, amplitude, crest, wavelength? B, amplitude, crest, frequency? C, crest, wavelength, amplitude? D, frequency, crest, wavelength? To answer this question, I think just look at your diagram that you were given and let's try to analyze it. So this distance from here, let's say this point is this horizontal line here represents equilibrium. So that is the position of rest, the position where your particles are undisturbed. That middle line there, that middle horizontal line is your equilibrium. So when your particle is displaced in the vertical direction, so it jumps from the position of rest, hence we say it is displaced because there's a change in position, especially in this vertical up and down direction. So it is displaced from equilibrium to a highest point. That highest point has a name. We call it the crest. Let me do this. Let me not write the crest to be there. So we call that highest point a crest, and it means that Y essentially shows the highest point on the wave, and that is the crest. But that displacement, that magnitude of displacement from equilibrium to the highest point also has a name, and it is referred to as the amplitude. Right? So we've identified X, we've identified Y. X is the amplitude, Y is the crest. This here, the distance, when we define the wavelength of a wave, the crest to crest distance or the trough to trough distance. So from the lowest point on a wave is called the trough. So even here we have another trough. We said the highest point is the crest, but the lowest point on that wave is the trough. And that trough to trough distance we can also define as a wavelength, typically represented by the Greek letter lambda. So it means Z is the wavelength. So now it's just a matter of looking through the options that we are given and seeing which one. So X is the amplitude, correct. Y is the crest, correct. And Z is the wavelength. It means option 1 is actually the correct one. And that is how essentially you will get your 2 marks. So when I downloaded this question, there was no memo that was provided. So I think it's important that we all go through these problems together. Do the calculations, check if what I'm saying is true based on the principles that we have learned in class or even on the channel. So now we go to question 1.2. In which one of the following do sound waves not travel? So one thing about sound is that it cannot travel in vacuum. Only electromagnetic radiation can travel in vacuum. Sound can travel in air, sound can travel in a liquid, and sound can travel in a solid. What is different is that the speed of sound in air, in liquid, and solid is just different. Sound is faster in solids and slowest in air or in gaseous substances. But sound cannot travel in vacuum. So the answer will be 1.2, and that's how you'll get your 2 marks. So now let's go on to question 1.3. Two pulses, X and Y, move towards each other at the same speed. The amplitude of pulse X is 1.8 meters and the amplitude of Y is 1.2 meters. The pulses meet at point R. I see here it's written at point R. So that instruction there, the last part of the instruction is hidden by that downloaded from stanmorephysics.com. So we're given a diagram representing pulse X, and this pulse X is moving from left to right. And then we also have pulse Y, and this pulse is moving from right to left. At some point, they're going to meet or they're going to overlap, and that is at the point R. And then we're given that the displacement of the particles from equilibrium, remember I said that horizontal line or horizontal position of no disturbance, that is your equilibrium. So from your equilibrium to the highest point, to the maximum point of displacement, that is your amplitude, 1.8. But also from equilibrium to the lowest point on that pulse, we can also say that is the amplitude of the wave or of the pulse. So now, when two pulses in the diagram meet at R, the type of interference and the resultant amplitude of the disturbance will be. So, because we have a crest here, the highest point, and now we have a trough here, the lowest point. When a crest overlaps with a trough, we have destructive interference. Let me write DI. So we have destructive interference. If a crest overlaps or meets with a crest, we'll have constructive interference, or similarly, if we have a trough, and a trough will also have constructive interference. So we can just look at the options that are given to us and start to eliminate. We have said this is going to be destructive interference. So that means that it can't be option C nor option D. The only options that we are left with is A and B. But now we know it's constructive. What about the amplitude? So if we have a crest and a trough that are overlapping or going through that constructive interference, or they are going through that phenomenon of superposition, they will minus. It means this amplitude of 1.8, we'll say 1.8 minus 1.2, which will give us 0.6 meters. So the amplitude will cancel each other out. And the option that gives us 0.6 is option A. It means the answer then becomes option A, and that's how you get your 2 marks. 2 marks over there. Let us now then go to question 1.4. This question is based on electrostatics. So we have that 1.4, two identical spheres A and B placed on insulated stands carry charges of plus 2 micro, so that is a Greek letter microcoulomb. Micro, remember, just means multiply by 10 raised to the 6 or negative 6 plus 6 microcoulombs respectively, as shown below. So sphere A has a positive charge of 2 microcoulomb and sphere B has a positive charge of 6 microcoulombs. When the spheres are brought into contact, so they touch each other, in which direction do electrons move? Do electrons move from A to B or from B to A? Or there's no movement as both spheres are positively charged? Or perhaps the answer is D, no movement. Electrons remain in A. So our options, we can eliminate both these options here, C and D. There is going to be a movement of electrons from one sphere to the other, even though both of these spheres are positively charged. And those electrons are going to go from the least positive to the more positive. So if we look, which one, A and B, so we will say this is least positive. If we compare, because both of them are positive, but this is more positive than the other. So electrons like to move from an area of high concentration to an area of low concentration. So it means here there is a least number of negative charges. Those are electrons in A, and here there is a more shortage of those electrons. So those electrons will be encouraged to move from A to B, and the answer will be A to B, and that's how you will get your 2 marks. The unit of measurement of electric current is ampere, and they are correct. Therefore, 1 ampere is equivalent to, we are given different options. So remember, the formula for current is that the current I equals to the charge Q measured in coulombs over the change in time, or delta T. So if it's 1, it means we just have 1. We said the charge on the unit of measurement for charge is coulomb, divided by the unit of delta T is going to be seconds. We can just simply also write this as 1 coulomb dot S minus 1. So we took this to the numerator, hence it had that power of minus 1. So if you look which options gives us 1 coulomb per second, and that option is B. So it means the answer will be B. Let us now go to question 2. Question 2. Let me see if I can see clearly. 2.1. The figure below shows a transverse wave motion. The period of the wave is 0.2. It's always important or nice to write what is given to you. So you know the period, capital letter T, is given to us is 0.2 seconds. It's the time taken to complete one full wave. The first question says, define the term frequency. So this is a definition, just a recall type of question. You can say the frequency is the number of complete waves per second. And this will make sense as we move along. I'll describe what that means just now. So this is how you will get your 2 marks for that question, by just knowing that definition. So it's important to memorize. It sounds bad when I say it, that you need to memorize, but when we are learning, typically most people start there in terms of memorizing, then you try to understand and you apply, then you go all the way up to the higher levels of cognitive understanding. But now the question now continues to say 2.1.2, you need to write down two pairs of points which are in phase. So points that are in phase on a wave is points that are separated by integer multiple of wavelength. The distance from a crest to a crest, we can agree that is the distance there, that is the wavelength. This also means that from here, from that point to this point F there, that is another wavelength. But if you also look, this distance from B to, let's say here, because that I see that point is not labeled. Let me just circle so that you see from there. It's actually equals also to this distance from A to D. It means also that distance is a wavelength. So you see this wave or this particle started there. If you're trying to understand the concept of a wavelength, it starts there, it goes all the way down, and when it returns to the same point, that is that it has completed a full wave. Now it means that points A and D are separated by one wavelength, so we can say that points A and D are in phase, but they said we must provide two pairs, so we need to find other points that are in phase. Points B and point F are also in phase because you see they are separated by this wavelength plus another wavelength, so that is 2 times wavelength. So points B and F are also in phase because points in phase are separated by an integer multiple of wavelength. So if points are separated by one wavelength or two wavelengths or three wavelengths, those points we say that they are in phase. The question then continues to say, write down the amplitude of the wave. So if you look, we said that the amplitude of a wave is always that the magnitude of displacement from equilibrium to the highest point or from equilibrium to the lowest point. So this distance here, if we call this distance, let's call this distance t, is also equals to this distance here t. Those two distances are equal. So if I wanted amplitude, it means I can just take this distance from the trough. The spelling there is off. So the distance from the trough, so that is the trough to crest distance to the crest, which is given to us as 30 centimeters and simply divided by 2, and I'll find the wavelength. So the wave there, not the wavelength, the amplitude. So the amplitude, you can just write A is going to be 30 divided by 2. 30 divided by 2, what goes twice into 30 is 15. So it means the amplitude of this transverse wave is 15 centimeters. So that's how you get your 2 marks. Calculate the 2.1.4 frequency of the wave. This question is requiring us to determine the frequency of the wave. So to calculate the frequency, we use the equation F equals to 1 over T. We know what T is. We already saw that it was provided to us in the question. So T is 0.2 seconds. So it means you're just going to say the frequency is 1 over T, which is 1 over 0.2. How many times does 0.2 go into 1? It goes 5 times. So it means the frequency is 5 Hz. So you'll get a mark for the formula, for the substitution, and for the final answer. Calculate the speed of the wave if the distance d equals to 3 centimeters. So we're going to use I'm trying to see where I can find space to do this question. So the distance can be given, the distance, let's say it's the change in x, is just the product of the speed. Oh, no. We are supposed to calculate the speed, not the distance. So the speed is going to be, the speed v is just going to be maybe the change in x, which is the distance, divided by the change in t, which is the time. So we already know the distance was given to us in 3 meters, but we don't know the time. Let's go find the time. So the period was given to us as 0.2. It means that the time for a complete wave is 0.2. So if we check here to here, that is a complete wave, it took 0.2 seconds. But also from here to there at F is 0.2. Because from B to F is actually the distance D. That distance D is the distance from B to F, which is about 2 complete waves, which took about, how long did they take? It took about 0.2 plus 0.2, which is 0.4. It's not necessary for you to show this step. I'm only showing it so that you understand where the 0.4 comes from. So you go then, you say, okay, I know now that so 0.43 divided by 0.5. I know the change in time. How much is that going to be? It's 0.4. We do this. So we have, it's a fraction. It's going to be 3 divided by 0.4. 7.5. So it means the speed of this wave to move from 7.5, always write meters per second. So the speed v equals to 7.5 meters per second. So the speed of that wave, how fast it's traveling between points B and F, which is the distance D, equals to 7.5 meters per second. Now we go on to longitudinal waves. 2.2. A tuning fork with a frequency 100 Hertz. That's one thing they're already giving you. They're giving you the value of F, which is there, 100 Hertz. Created a sound wave as illustrated in the sketch below. There's the sketch. We see somehow between these points, which are defined by R, the particles are much closer together. If we take these individual dots as particles, the particles are much closer together. And then here, those particles are a bit far apart from each other. And the first question is, define a longitudinal wave. What is a longitudinal wave? A longitudinal wave, right? A wave in which the particles of the medium vibrate parallel to the direction of motion of the wave. So that is how we typically define a transverse wave. So it means if the wave is moving in this direction, the particles are also going to be displaced in this direction. If the wave is moving in this direction, the particles are also moving in this direction. So that's what a longitudinal wave is, and sound is a form of a longitudinal wave. Now we have to label the parts labeled R and S. So the parts labeled R, where the particles, it's a high pressure area where the particles are closer together. we call that a compression of a longitudinal wave. And where these particles, it's low pressure, they are not close to each other, we call that the rarefaction. So it's important for you to rarefaction. I hope this is the right spelling. It's important for you to know those, to be able to label and identify a rarefaction and a compression when given a diagram of a longitudinal wave as it has been done here. And then question 2.2.3, calculate the period of the sound wave produced by the fog. So the nice thing about frequency, so remember in the other question we said that the frequency is 1 over t, but this also means that the period t is equals to 1 over f. These two values are inverses of each other. So we have 1 over. That's why we say it's an inverse. It means that the period is inversely proportional to the frequency. If the other one increases, the other one decreases. So it means t equals to 1 over 4, 1 divided by 100. How many hundreds are in 1? That will be 0.01. Let me double check. So we have 1 divided by 100. So that is 0.01. So 0.01 seconds. So it means the time it takes to complete one full wave or full wave pulse is 0.01 seconds. It's very fast. 2.3. We now have a group of students or a group of scientists. I don't know why I read student on board a submarine, and they want to locate a whale. A signal generator on a submarine sends a wave signal underwater, and a detector detects a wave reflected from the whale 3 seconds later. Now, the speed of sound, so we're given the change in t, is equals to 3. The speed of sound in water is 1,480 meters per second. I think that is what is written there. So v, the speed of sound is 1,480 meters per second. So we have a submarine over here. It sends out a signal because we want to determine, to locate, to find where exactly is this whale. So it will send out a sound signal. Remember, sound can be, waves can be reflected. So it will send out that signal all the way. The signal will encounter a boundary caused by the whale over here. And then part of this sound is going to be reflected back. So we have a signal, and then part of it is reflected back. Now, after about 3 seconds, that's when we detect the signal. We send it, we wait, goes to the whale, gets reflected, comes back, and finally we detect it here at the submarine. And now the question is, we need to calculate how far in kilometers is the whale from the submarine. So we need to find this distance, the distance from the submarine, let's say, to the whale. Let's call that the distance d, and we need to find where is it in kilometers. This is actually a very interesting problem, and using the sound, is it sound navigation and ranging, something called sonar. Dolphins, bats, they use this ability of sound waves to be reflected to essentially locate or to travel, to navigate their surroundings. That's what I mean. So it's sound navigation and training. Sound navigation and ranging, sonar. Now I'm getting distracted. The question says, calculate how far in kilometers is the whale from the submarine. So the distance d, let's call that the distance d. The distance is always the product of the speed multiplied by the time. At the back of your question paper, they would have given you a formula like change in x equals to v times the change in t. The change in x typically means the distance, v is the speed, and the change in t is just the change in time. But one thing that is important about these types of question is that you need to realize that the signal travels 2 times the distance, because it travels from the submarine to the whale, and it travels back the same amount of, so if it traveled 5 meters to the whale, it will travel another 5 meters. It means the total distance it traveled was 10. So that's why we include a 2 there. So 2d equals to the speed times the time. So then you'll have that d. To find d, we simply divide both sides by 2. What you do on the left, you do on the right. So that d, the distance d, is the speed. I need to learn to write better. Time divided by 2. That looks nicer, right? So we have the speed, which was given to us as 1480, multiplied by the total time it took, which was 3. Was it 3 minutes or 3 seconds? It was 3 seconds. So 3 seconds multiplied by 3, and the whole thing must be divided by 2. So 1480 times 3, all of it divided by 2. So put that in the calculator. You say, okay, 1480 multiplied by 3 divided by 2. And this gives us a value of 2220. 2220 meters. But remember, the question said we must provide the answer in kilometers. So to move from meters to kilometers, from a lower number to a higher, I don't want to say number, from a lower unit of measure, which is the meter, to a higher unit of measure, I stand corrected in that assessment. So you just divide by 1,000. It means to get the distance in kilometers, we'll just say it's 2220 divided by 1,000, which is going to be equals to 2.22 kilometers. Remember, we're always rounding off our answers to 2 decimal places. It's 2.22 kilometers. See, my calculator has disappeared. Let me bring it back. Let's go to question 2.4. The diagram shows 2 sound waves measured for the same interval. So we have for the same time interval. So what they are essentially telling us is that from here to here, we can just decide that the time it took is 1 second. So both of this wave A, see wave A there, I don't know why this is not drawn in different colors. Then we also have wave B. They have the same in time interval. And now question 2.4.1 is saying which one, trying to see if I can, how do I make it? Okay, nope. Just trying to see if I can erase without having to click there. I think I can, I've just forgotten how to. So which one of the sound waves A and B has a higher pitch, and explain your answer. So we have, is it A or B? So remember, the pitch of sound is related to the frequency. So the pitch is directly proportional to the frequency. So the pitch of sound is directly proportional to the frequency. It means the higher the pitch or the higher the frequency, the higher the pitch. So, but how, when we are given a diagram, how do we decide? How do we know? How do we tell the frequency? Remember, the frequency is the number of completed waves, the number of completed waves in 1 second. So if we said from here, the whole time interval we decide, you can decide it to be 1 or 3. I just decided it to be 1 second. So if from here to here is 1 second, we need to check which one completed more waves. Is it A or B? So we'll say we started here with a B, and it goes all the way down. And then here the first wave is completed. Then it starts, let me make a different color, feeling like red. There's another wave. Ooh. Another completed wave, and then we'll get at the last half wave from here until there. So we have about how many completed waves are in there. We'll say it's 2.5 because we have 2.5. But let us have a look for A. For A, we have that wave. It goes all the way down, and then it goes, so that's the full wave. And then we'll also now have another half wave going from there to there. So B has about 1.5 waves. So which one has the highest frequency? The one that has the highest frequency is the one that has completed more waves in the given time interval, and that is B. So it means that B has a higher pitch. So you write B, you'll get a mark. And why? Pitch is directly proportional to the frequency. The higher the frequency, the higher the pitch. And now we have question 2. I see they said 2.2.2. Supposed to be 2.2. Supposed to be 2.4.2, right? When you're writing, it's either you lift your hand to alert your invigilator about the mistake, but typically write it as 2.2.2. And then it says which one of the following sound waves, A or B, is louder. So the loudness of sound is directly proportional. So that loudness of a wave is directly proportional to the amplitude. That means the higher the amplitude, the higher the louder the larger the amplitude, the louder the sound, proportional to the amplitude. Right. So which one between A and B has a larger amplitude? So the amplitude for B will just be this displacement, the magnitude of the displacement from here to there, which is the crest, and the amplitude for A will then be that. And you can already see that A actually has a higher amplitude. So the answer there will just be A, just 1 mark. Let's go to question 3. Question 3, can see we are looking at electromagnetic radiation. Question 3, the three appliances which emit different types of electromagnetic radiation are shown below. We have the TV remote, the TV remote control, which is this one. We have the red laser pointer that people use when they give presentation. This, when I change the channel. You also have the microwave. After school, the pap is dry, put it in the microwave to warm it up. So 3.1. So we are here at question 3.1. So question 3.1 says, state the type of electromagnetic radiation which is emitted by the television remote control. Go memorize the electromagnetic spectrum, the different types of electromagnetic waves or electromagnetic radiation, and at least know one common use of each of them. What is the use for gamma rays? What is the use for X-rays? What is the use for UV? What is the use for visible light? What is the use for infrared thing? What is the use for microwaves? What is the use for radio waves? All of them. So television remote controls, they use that infrared radiation. And the laser pointer, which electromagnetic radiation is used there. You see that that laser pointer emits a red light. So that tells us it's visible light. Visible light is a type of electromagnetic radiation. So that's how you'll get your answer. A television, 3.2, a television, I'm not sure why this is not moving. A television remote control emits photons with a wavelength of 320 terahertz. Question 3.2.1, define the term photon. The term photon simply refers to a packet of energy found in light or in electromagnetic radiation. Remember, light is a form of electromagnetic radiation. So it's just a packet of energy. That is the simplest definition of a photon. Go memorize those definitions. Now, question 3.2.2. Calculate the energy of a photon emitted by the television remote control. So that television remote control, it was mentioned that it emits a frequency of about, how much is that? It's going to be 320 terahertz. Now we need to determine the energy of that photon that is emitted by that. So this is pretty straightforward. We have an equation E equals to, let's see, we have an equation E equals to HF. We know that the frequency F is 320 terahertz. Tera means multiply by 10 raised to the power of 12. So it's important to also know those prefixes. H is a constant. Given this value at the back of your question paper, let's have a look. There it is. H, 6.63 multiplied by 10 raised to the power of minus 54 joule second. So I also have that it is 6.63 multiplied by 10 raised to the power of minus 54 joule second. So this is straightforward. As I've mentioned, E is equals to 6.63 multiplied by 10 raised to the power of minus 54. That is multiply, if we put it in a bracket, 320 multiplied by 10 raised to the power of 12 hertz. And that gives us, let's see, put it in a calculator. Please confirm this calculations for me. like I said, I don't know if I've mentioned, this question paper doesn't have a memo. 10 raised to the power of minus 54. So it is up to us to do this, to solve the problems correctly. If you see that I've made a mistake somewhere, please let me know. I like feedback because this is the only way we learn, if we have feedback and we grow. So that's 2.12 to the 19. It's 2.12 multiplied by 10 raised to the power of minus 19 joules. Energy is given in joules. So you get a mark for the formula, for the substitution, and for the final answer. Maybe you get 2 for final answer. That's why it's 4. And then we have question 3.3. A microwave emits the waves with 2 multiplied by 10 raised to the power of minus 23 joule of energy. Calculate the wavelength of these microwaves. So just gonna write just below there. I'm gonna draw a line. So we are given, what is it that we're given? We're given the energy. It's 2 multiplied by 10 raised to the power of, is it minus 24? Minus 23 joules. And we need to find the, what is it that we need to find? We need to find the wavelength. So our equation, which is E equals to HF, we can remember we also have another equation, C equals to F lambda. This is the speed of electromagnetic waves in vacuum. This is the frequency, and this is the wavelength. So it means we need to relate these two equations to each other. How do we do that? A matter of making F the subject. If we make F the subject, we simply divide by the wavelength on both sides. So this wavelength cancels that one, such that we are left with that F equals to C over lambda. Now we take this expression and we put it where we see F. This now means we'll have H. What is our F? C over lambda. This equation as it is actually given to you at the back of your question paper, HC over lambda. Let me show you. It should be given. See, there is the equation I'm talking about. So you don't need to know particularly how to derive it, but it's always important to understand where things come from. Don't just make up things on the spot. Something always comes from something. But we need to then solve for the wavelength. And to do that, it means we just multiply. I can make this a fraction, just cross multiply. So I'll say, okay, the wavelength multiplied by E is going to be E times wavelength. And 1 multiplied by HC is just HC. I want to make lambda the subject. I just divide both sides by E. It means the wavelength is going to be HC over lambda. Some people prefer to do this process once they have substituted in the values. It's the same thing. I personally prefer to do it beforehand because I think with values it's so easy to lose track because you're working with very large or very small values over here. So it means the wavelength is going to be the Planck's constant, 6.63 multiplied by 10 raised to the power of minus 34 multiplied by the speed of electromagnetic radiation in vacuum, which is 3 multiplied by 10 raised to the power of 8. All this divided by the energy in joules, 2 multiplied by 10 raised to the power of minus 23. It means the wavelength is going to be, you need to put this in a calculator. Let's see. Open those brackets. You're working with very small and very large numbers. So those brackets are your best friends. If you don't, you will quickly lose track and you'll wonder, I did the steps correctly. However, I got the answer wrong. If you make a mistake, the calculator will also give you the wrong answer. So brackets 2 multiplied by 10. It is starting to rain. I might have to stop. 23. Is it 23? Yes. Everything perfect. So the answer that I get is 9.95. We must do this to two decimal places. It's 9.95 multiplied by 10 raised to the power of minus 3 meters. So that is the wavelength. So because you are given the equation, you get a mark for providing it, showing that you understand the substitution. And I think the final answer may give you about 2 marks. Question 4. Two identical metal spheres A and B are placed on insulated stands. Spheres A carries a charge of plus 4.4 nanocoulombs, that N is for nano, and sphere B has 1.25 multiplied by 10 raised to the 10 excess electrons. So we have sphere A there with a positive charge of 4.4 nanocoulombs. We have sphere B with an excess of electrons. It means it's negatively charged because it has an excess. It has more electrons than it does protons. That's why we say it's an excess. It has extra. So it's going to be negatively charged. We just don't know what the charge is, but we are given the number of electrons, so it means we can be able to calculate it. And the first question is 4.1. State the principle of charge quantization. State the principle of charge quantization. So the principle is that the idea behind charge quantization is that all the charges in the whole universe, consists of an integer multiple of the charge on one electron. Let's say on one electron, or a single electron. Integer doesn't have an R. Electron, I don't know. So all the charges in the universe consist of an integer multiple of the charge on one, not on A, on one electron. So the charge on one electron is this value over here that is given. See that value there, that E. There's the charge on it. It's minus 1.6 multiplied by 10 raised to the power of minus 19 coulombs. I typically write it as QE, Q with a small letter E. So it's minus 1.6 multiplied by 10 minus 19 coulombs. So sometimes you will check your formula sheet and you find that they've written it as a positive number. This is the thing. If your calculations involve, they tell you the number of excess protons, you'll use this. Remember, protons are positive, so you will actually use this value as positive. But if we're talking about electrons, use it as negative. So when they say that all the other charges in the universe are just actually a multiple of this value, so it means that every other charge, if you measure anything with a charge, you'll find that it's the value of in coulombs is just either 1 multiplied by that QE value, or 2 multiplied by that QE value, or 3 multiplied by that QE value, or 4 multiplied by that QE value. You're starting to understand where I'm going with this, right? So every other charge, all the charges in the wave, they consist of an integer multiple of the charge on one electron. And that is, in a nutshell, the principle of charge quantization. Such a nice thing to say, charge quantization. So they're saying to us, let us calculate the amount of charge on sphere B. So what is the amount of charge on this sphere? So the amount of charge Q on this sphere, when we are given that, we know that QE equals to minus 1.6 multiplied by 10 raised to the power of minus 19 coulombs. We know the number of electrons or number of excess electrons, which is 1.25 multiplied by 10 raised to the power of 10. We need to find Q. So which equation relates all of these things together? If you go at the back of your question paper, you'll find an equation that writes something like Q equals to NQE or Q equals to NE. Let me check how they wrote it in this question paper. It's Q, going for electrostatics. There we are, Q over E. That is the same thing. So we will say, okay, to find the charge Q, we simply multiply the number of excess electrons, which is 1.25 multiplied by 10 raised to the 10. We multiply that by minus 1.6 multiplied by 10 raised to the power of minus 19. And that is going to give us. So we then have 1.25 multiplied by 10 raised to the 10 brackets minus 1.6 multiplied by 10 raised to the power of minus 19. And we check how much that is. That is going to be minus 2 multiplied by 10 raised to the power of minus 9. So it means that the charge on sphere B is minus 2 multiplied by 10 raised to the power of minus 9. The SI unit for charge is coulombs. So that is the charge there. We can just write there QB for the charge on sphere B, which we have calculated now as 2 multiplied by 10 raised to the power of minus 9 coulombs. So you will get your mark there for that formula of charge quantization, the substitution, and the final answer. Write down the name of the type of field around the charged spheres. Choose from magnetic, electrical, or gravitational. The answer to this is obvious because with electrostatics we're dealing with electric charges. So around charged spheres, for example, let's say a positive sphere, we will have an electric field that is moving away from the charged sphere. So we move something like this, so it is outward. But around a negative charged particle, we will have that electric field pointing towards. I'm not sure in which term you're gonna start learning about these electric fields are surrounding charges. Perhaps it's going to be done in grade 11. I'll have to double check with the ATP. So now, give a reason why the charged spheres are placed on insulated stands. So remember, we have things that are called conductors. We have conductors. And we also have opposite to conductors, we have insulators. In conductors, electrons are free to move. Electrons move freely. So example of conductors can be metallic wires. In insulators, electrons are really not free to move. Doesn't mean that they can't move at all under certain conditions, but it's very difficult. So aren't free to move. So that is the main distinction. An example of an insulator will be a material like glass or rubber or even plastic. But that's not what the question was asking us. The question was asking, why do we put these charged spheres on insulated stands? This is to avoid charges, negative charge, which is carried by electron, from moving into the insulator. From moving. So if that insulated stand if that insulated stand, remember you have a charged sphere, the circle, and then there's the insulated stand. If now this was a conductor, electrons would move either to the stand or from the stand to the sphere. We don't want that to happen. So to prevent the flow, let me not say, to prevent the flow of charge to the stand, so to prevent these charges from moving, we then rather use an insulated stand. In an insulated stand, we know that charge cannot move. So that is the primary reason why we put these conductive spheres on insulated stands. So we go to question 4.5. The spheres are brought into contact, meaning they touch, and then separated is shown below. So we have here, they are in contact, A and B. As you can see, they are touching. When they touching, they will transfer electric charge. So charge will move from one sphere to the other. It can either move from B to A or from A to B. And then after a while, these two spheres are going to have the same charge. So they might have a charge of 2 coulomb, and then they will be separated. Question 4.5.1. State the principle of conservation of charge. What do we mean when we say that charge is conserved? Think about it. What do we mean when we say anything is conserved? Mass is conserved. Charge is conserved. Momentum is conserved. I think in metric you learn about the conservation of momentum. So the principle of conservation of charge is that the net charge of an isolated system does not change. An isolated system remains constant. When we say it remains constant, it means it doesn't change during a physical process. So a physical process may be what we saw above, whereby the spheres were touching. So that may potentially be something that can be classified as a physical process. So what this thing is telling me, let's say for an example, you had initially a charge of 2 coulomb on sphere A, and you had a charge of 4 coulomb on sphere B. Let's say before they touched. After they touch, you will have a charge of 3 coulombs and 3 coulombs here. Realize that the total charge, or the net charge, so when we talk about total, we talk about net. So before touching, it was 2 plus 4, which is 6. After touching, it is 3 plus 3, which is still 6. So the net, the total charge of an isolated system does not change during any physical processes. Yes, the charges on the spheres might change. However, the total will remain the same before and after that physical process, before and after touching. So that is in a nutshell what that principle of conservation of charge implies. And then you will get your 2 marks there for writing that, for stating that principle there. 4.5.2, which sphere loses electrons when the spheres are in contact? So are electrons moving from A to B, or are they moving from B to A? So if we remember correctly, let's see, we said that the number of electrons, I'm lying the charge on sphere A, let's call it QA. How much was it? Let's go check. That charge was 4.4. It is 4.4 multiplied by 10 raised to the power of minus 9. And the charge on B, right, QB, equals to minus 2 multiplied by 10 raised to the power of minus 9 coulombs. So that is the charge. So a sphere which is more negative, or which has more negative charge than the other sphere, that is the sphere that was going to transfer the electrons. So we see that this sphere carries a negative charge. It means it has an excess of electrons. So those electrons are going to want to move. It means that electrons are going to move from sphere A to sphere B. So which sphere loses electrons? If electrons are moving from sphere B to sphere A, it means sphere B loses electrons, and you get your mark. Remember, it is the electrons which are that move, not the protons. Calculate how many electrons transferred from one sphere. Calculate how many electrons are transferred from one sphere to the other when they come into contact. So you need to find how many electrons are transferred. To do this, we first need to figure out what is the charge here after touching. What is the charge here on sphere A after touching? So what is the charge here after touching? What is the charge here? So we do that by using our equation Q, which is our principle of charge conservation equation, which is Q1 over 2. It means that the charge after touching on each sphere will be equals to Q. So you see, we take the total charge by adding the charges on one sphere before touching plus the charge on another sphere before touching, and we divide it by 2. And this will tell us how much charge is on each sphere after touching. So we know in this case we have QA plus QB divided by 2. What is the charge on QA? The charge on QA is 4.4 multiplied by 10 raised to the power of minus 9. The charge, and then we say plus, there's a plus there, brackets. The charge on sphere B is minus 2 multiplied by 10 raised to the power of minus 9. And all of it must be divided by 2. So we can just put this in a calculator. So we have 4.4 multiplied by 10 raised to the power of minus 9 minus 2 multiplied by 10 raised to the power of minus 9, and that whole thing we divided by 2. And we see that we calculate that the charge on each sphere after touching equals to 1.2 multiplied by 10 raised to the power of minus 9 coulomb. So after touching the sphere QA, after touching, is going to be 1.2 multiplied by 10 raised to the power of minus 9 coulombs, and the charge on sphere B as well is going to be 1.2 multiplied by 10 raised to the power of minus 9 coulombs. The charges will be the same. This is for identical spheres. But we are not asked to calculate the charge after touching. We are asked to calculate the number of electrons that are transferred from one sphere to the other. And to do that, we need to find the change in Q. That change in Q is going to tell us the amount of charge that is transferred. So we'll say, okay, QF, I'm not sure if this is available at the back of your question paper, minus QI. So we'll take whatever sphere we want. I personally prefer that you use the sphere that the charge is being transferred to determine the charge, the amount of charge that was transferred to it. I've seen when you use the other sphere, the value will have the value will have an opposite sign. So if you use the sphere in which the charge is being transferred to and you get a positive value, then you use the other sphere in which the charge was transferred from, you get a positive value. So just for myself, use the sphere in which the charge is being transferred to. We've already established that the charge is being transferred to sphere A. This means that we will say the change in Q is going to be QF on A, on sphere A, minus QI on sphere A. QF is the final charge, which is this charge over here of 1.2 multiplied by 10, which is raised to the power of minus 9, minus Q initial is the charge on the sphere before they touched, which was positive 4.4 multiplied by 10 raised to the power of minus 9. And this will give us the change, the amount of charge that is transferred. How much is that? If we put that on the calculator, where is my calculator? Okay, I can find it. Let me pause. So we have that 1.2 multiplied by 10 raised to the power of minus 9 brackets minus 4.4 multiplied by 10 raised to the power of minus 9, and we find that the amount of charge that is transferred to sphere A is minus 3.2 multiplied by 10 raised to the power of minus 9. So we said that value is minus 3.2 multiplied by 10 raised to the power of minus 9 coulomb. We still have not calculated the number of electrons. Yes, we know the charge now that is transferred, but we don't know the number of electrons. Which equation do you think we're going to use to find the number of electrons? We've already used it before. So we will use our charge quantization equation, which is Q equals to NQE. This is the charge on an electron. We know the value of it. We know now Q, or we can rewrite it as the change in Q. The change in Q is the amount of charge which is transferred, which is equals to NQE. We can rearrange this. When we rearrange, we will find that the number of electrons is given by the change in Q divided by QE. So what is the change in Q? It is minus 3.2 multiplied by 10 raised to the power of minus 9. All of it divided by minus 1.6, that is the charge on a single electron, minus 1.6 multiplied by 10 raised to the power of minus 19. A negative divided by a negative is going to be a positive. So whatever value we get is going to be a positive value. So we will say, how much was that? Trying to move this so that we can see. So it's a fraction. On top, you say minus 3.2 multiplied by 10 raised to the power of minus 9. All of it divided by minus 1.6 multiplied by 10 raised to the power of minus 19 coulombs. And you find that value to be 2 multiplied by 10 raised to the 10 electrons. There's a lot of electrons. So you have 2 multiplied by 10 raised to the 10 electrons. So that is the number of electrons that is transferred during contact from sphere B to sphere A. So it is a particularly long question. That's why it is out of 5. Someone could have done it quite differently. I just did it step by step so that you can see why I do certain things. It's a very interesting question that typically pops up in questions, in question papers, or in exam test questions. Let's go to question 5. The circuit diagram below consists of a battery, a switch, an ammeter, and a glowing light bulb, all connected in series. A voltmeter V is connected across the light bulb. So one thing that you need to know, most elements, so we have a battery, let's start there. You have an ammeter, so it measures the current I. It will tell you how much current is in the circuit or how much current is in a circuit element. So the battery is the power source. It gives the electrons the energy, the juice, so that they can the charges can be driven around the circuit. So it's the power source. And then you have a light bulb. So that's your light bulb. They're saying it's glowing, meaning it is on. So your light bulb is a load. It uses that energy that the battery gives to the charges. It uses it. So that's why we say it is a load. And then we have a switch. A switch can be open or closed. In this instant, it is closed. And then we also have a voltmeter. A voltmeter measures the potential difference across a circuit element. So see the keyword there. They tell you that that voltmeter is connected across. That tells you that it's connected in parallel. And it is always connected in parallel to whatever circuit element we're trying to measure the potential difference of. So if you see, it is connected across, there it is, it's connected across the light bulb. So it means this voltmeter is going to tell us the value of potential difference between of the light bulb. Why? If you connect two circuit elements in parallel, they will experience the same potential difference. So if you have a potential difference of 2 here, the voltmeter will also have a potential difference of 2. Hence, it will be able to tell us how much potential difference is actually at the light bulb. If you connect a circuit elements in series, they told you the battery, the ammeter, and the light bulb are all, and the switch are all connected in series. It means they're going to have the same current. So the ammeter is always connected in series because we want to know the current. So it means this ammeter will tell me the current. It will have, if the current there at the light bulb is 2, the current also here will also be 2 amperes. If the current that is going through a switch is 2, it will also, the ammeter will also have a current of 2. If the current through the battery is 2, I'm just making examples here. The ammeter will also have a current of 2. So it will be able to tell us how much current is going through either the whole circuit or a specific circuit element. Right? So let's continue. What is the question saying? The first few questions are definition questions. 5.1, define the following terms. So we need to define potential difference. Potential difference is the energy transferred per unit charge. The energy transferred per unit charge, per unit electric charge. Some people might say it is the work done per unit electric charge. Electric current, we define it as the rate of flow of charge. So how fast is the charge flowing in that circuit? So that's how you get your 2 marks. So that's 4 already. Then we are told that the reading on an ammeter A is 0.6 amperes. Always check if it's in the correct SI unit. It's not kiloampere or milliampere. If it is, then first convert to the right SI unit. 4.86. So before I move ahead of myself, if the current through that ammeter is 0.6, so I equals to 0.6 amperes, it means also, because it's connected in series to this light bulb, the current through that light bulb is also going to be 0.6. So we now know the current through the light bulb. That question continues to say 486 joules of energy is transferred to a light bulb. So every time energy is transferred, we talk about transfer of energy, you must know that work is done. When time we transfer energy, work is done. Remember, perhaps early, maybe somewhere when you started doing natural sciences, we were asked to define energy. So energy essentially refers to an ability of an object to do work on another object. That is to move that object a specific distance. So that is why when we do work, we transfer energy. We transfer energy because you need energy. So when you're transferring energy from one object to the next, from a battery to a charge, work is done. When your charge is moving through this light bulb, it transfers its energy because the light bulb uses its energy. So the energy is transferred to the light bulb. It means work is done. Hope that is clear. So it means the work done also is given by W equals to 4. Work done is represented by W, 486 joule. Let me write it there at the bottom. So the work done by charges on that light bulb is 486 joules. And this process, they're saying, takes about T, or delta T, the change in time, takes about 3 minutes. So, but we know 3 minutes, for delta T, the SI unit is seconds. It means we need to convert minutes to seconds. So we just simply multiply by 60. 1 minute equals to 60 seconds. So it is 180 seconds. And now we need to find what is the reading, what is the voltmeter going to say is the voltage or the potential difference across that light bulb. We know that the potential difference is given by the work done per unit charge. So W is for the work done, Q is for the charge. From We also have an equation for current, which is it is Q over delta T. So we need to relate these two equations together. So I see there's Q here, there's Q. I'm going to make, I have the current, I have the change in time. It means I can find Q. And if we use this nice triangle, we find that the current I equals to Q in the numerator divided by delta T in the denominator. So if I want to find Q, it means my Q is going to be I multiplied by delta T. So I'm like, oh, okay, now I know the value for charge. I can essentially take this value and substitute it there by Q. Or somebody might decide to first calculate it. I won't do it. And then only plug in the value after. So at V, we'll say it is equals to W divided by Q, but we said Q equals to the current multiplied by the change in time. We have all of these values. We have the value for the work done W, the current I, as well as the change in time. So we find that W is equals to 486 divided by the current. What was the current? It's 0.6 multiplied by 180. Let's see how much is that. So we have 486 divided by 0.6 multiplied by 180. I could have still put the top part in brackets as well for consistency, right? So this is 9 over 2. 9 over 2 is just 4.5 volts. So that is 4.5 volts. You don't need to write it in full. You can just write 4.5 V. This means that the potential difference across this light bulb is 4.5 volts. The question is 6 marks. It tells you from scratch that you're going to have to do a lot of work. Typically, you will be using 2 equations or sometimes 3, and you just need to find what is common, which was the charge, and that charge we can calculate because we are given the current and the change in time, and that value we just put it here. When we have that value and we also have the value for work, we can determine the potential difference. And this brings us to the end, actually, of this question paper. Let's see. Yes.